Hello, BC students. Are you ready? Excuse me. Reviewing, what are we reviewing? Units 7 and 8 today. We'll do 9 and 10 in mixed review tomorrow. And we're going to get you ready to show what you know, which is a lot. All right. I don't have the test graded. I apologize. It'll be probably Saturday before I get to it. And I understand you want to know where you are grade-wise, and I'll do my best this weekend to get you there. And we'll go from there. We'll see them when we see them. So I know you're anxious, but right now let's just focus on the calculus, shall we? All right. So Unit 7 is differential equations. It's a big part of calculus. It's the idea of focusing on the rate of change of a mathematical relationship rather than just the amount of the function itself. And from the rate of change, we can make lots of inferences about the function itself. So let's start there. First of all, you should be able to model situations with differential equations. Based on how something changes, you would know about how something behaves. Usually, when you say differential equations, you talk differentials or Leibniz notation. But it is common that you will sometimes see y or y prime. You will not see function notation here. So you won't see f prime here because that does not imply any kind of differential equation. So dy dx, y prime or y double. Many books use that y prime notation, including the Rogowski books that they use at Mines. So I want you to be aware of that. But it's the same as dy dx implied, all right? Verifying solutions for differential equations. I have an example of that. That is definitely not done in our book, and we need to practice that. But it's kind of like an identity for calculus. And we'll get to that. Sketching slope fields and reasoning using slope fields. I don't feel like you guys have trouble with that, so I'm not going to hit it. Although if you want to review it, I'll just drop me an email and I'll drop it in somewhere. Approximating solutions using Euler's method. Now that's a BC only idea, and so it's a pretty big idea that is easy to incorporate into other questions. So I think it's a good bet that you'll see it on Tuesday. The idea is basically making an inference about a new y using an old y and the rate of change, or the differential equation, which is why this isn't a differential equation idea, all right? Remember, the step size goes from an x old to an x new in some number steps. The step size then is the new minus the old divided by the number of steps. If it's the case that you're going to a smaller number, for example, you know x at 2, but you want to estimate what's going on at x of 1, then your delta would be negative. Yeah, that's obvious. The idea, by far, and you should show quality work, is y old, that might be y2 or y3 or whatever, is, let's just call it y new, excuse me. Yn plus 1 is the previous y, whatever it might be, plus the rate of change at the previous x and or y times an amount of change in x. All right. Think of it like a tangent line on steroids. It's multiple tangent lines making lots of recalculations. All right. Finding general solutions using separation of variables. That is crucial, that you separate the variables. And so say you had some kind of x relationship and a y relationship. I don't even want to use function notation because I don't want you to get whacked out. Some you have x stuff. That's far less mathy. And y stuff, you've got to show separation of variables. So dy and the y stuff, dx and the x stuff, whatever it might look like. All right. When they say find particular solutions using initial conditions and separation of variables, that's key. Now, you guys are awesome with the fundamental theorem, But if you are given a differential equation and an initial condition, do not use the fundamental theorem, which is to say, do not do y initial plus this kind of deal. This is not separation of variables. It's often not the case that the function is based in the dependent variable, which is only what the fundamental theorem is used for. Do not use it, okay? If the equation is differential equation, then separate the variables and get a plus c and use the initial to find a plus c. Do not use the fundamental theorem, understood? The first step in those rubrics is often separates the variables. If you use fundamental theorem, you're not separate the variables, you get 0. All right? Exponential models with differential equations. The biggest is the exponential growth model, which is to say, I always think compound interest. When I think how much my money grows in compound interest, it grows at a rate that's proportional to how much I have. Obviously, it matters, if I'm making 10% on my account or 20%, that's the K. But really what matters is how much is in my account. 10% of $5,000 will grow by 500, but 10% of $50 will grow by 5. So obviously how much it changed depended on how much I had, not time so much, but how much I had. So this idea that growth rate depends on how much you have of the dependent variable is unique to exponential growth, all right? It implies the exponential growth or decay model. Remember, K is positive, implies exponential growth. K negative implies exponential decay, all right? You also need to attach the verbal statement to that. Amount grows or decays at a rate proportional to the amount. All right, the logistic model. It's been a while. Set 115. Remember, the idea is the amount of population growth depends on how much population there is, and so that's like exponential growth, but how much room for growth there is. Think carrying capacity. P represents the carrying capacity. If this is not just P, then, for example, sometimes you'll have a fraction under that. You should factor first, then look at the carrying capacity, because the carrying capacity isn't necessarily what's here if this isn't P. So first, make this P, then look at L to determine the carrying capacity, all right? Factoring also will make or affect the K. As far as the actual exponential or logistic equation model, which is this guy, L over 1, the good news is I haven't seen one single free response nor multiple choice that required you to know that. So we're going to let that go. Although it's good stuff to know, it's important. Mostly they focus on the differential equation that you need to know. Let's go a little bit more on a picture. Remember, on logistic growth, the star of the show is the inflection point. This is population at time. This here, upper limit, is the carrying capacity. Remember, fastest rate of growth when the population is half the carrying capacity. Also, remember two ideas on the graph, and that is, as time goes to infinity, the population approaches L, and as time goes to infinity, the rate of change, dp dt, approaches 0. Right? Those are two big ideas. And I think that's all on the notes I wanted to hit. So let's move on to practice, shall we? So same as always on the practice. Pause the video, try the problem, and then hit play to see how you did. Go ahead and go. Okay, so let's see how you did. Your answer is C. C. If you killed that, then move on to the next question. If you did not get that or you were iffy on that, then let's talk about it. These are the problems that are kind of like an identity. You're trying to show that this could come out to be 6 based on one of these equations. So for example, on this, if I found y prime that was 2x, and then I plugged in the left to see what I got, xy prime would be x times 2x minus 3 times y is x squared plus 2. So if I substituted in y prime and y, do I get something that would come out to be 6? Well, you can see the x squareds would have to go away, and they don't. 2x squared minus 3x squared is still left, and you do not have 6. So that's not true. Let's go with this guy. Y prime is 6x. Therefore, xy prime is x times 6x minus 3y is 3 times 3x squared minus 2. Same kind of deal. 6x squared minus 9x squared does not go away, so that's a no. This one, y prime is 15x squared. Therefore, xy prime is x times 15x squared minus 3 times y is 5x cubed minus 2. That does work out. 15x cubed minus 15x squared plus 6 is 6. And so that is true. And you can verify the last one, but you'll see it. See. All right. Try this one. Pause the video, give it a go, and we'll see how you did. I know it says which of the following could be the logistic, but I stripped off. Let's just say, what is the logistic differential equation, right? The differential equation, not the amount equation, the differential equation. So dp dt. All right, so my answer is dp dt is 1125 p times 500 minus p. If you agree with that, then, and you have no questions, feel free to move on. If you don't, pause the video and get out the red pen. Let's go. All right, so number of students in a school heard a rumor. I get it. It could grow exponentially because one person tells 2 people and 2 people tell 4 people. I understand the exponential growth component, but there is a limit to this. How many students can, so that's why it's logistic, not exponential. There's only so many students, right? I understand the idea, the big context. Now, I start with the logistic differential equation, which is this. All right, and I try and figure out what do I know. I need to find this and this to make my specific equation. All right, dp dt and p stay variable. All right, let's go with L. L is the carrying capacity. How many students that are possible to hear the rumor is 500. So that is where I came from there. All right, now the other one was definitely harder. That might have been what you had trouble with. You were fine with the 500. Also at noon, P is increasing. So you know 2 things at noon. How many students have heard the rumor? Now that's P. P represents the number of students who have heard the rumor, and increasing at a rate of, that's the rate of change. So this, the rate of change is 20 when P is 50. That's where I got the 1,125, assuming I did the arithmetic right. That's where that came from, all right? All right. Sorry about the poor cutting and pasting here. Dumb. All right. Which of the following is a solution to the differential equation with the initial condition? Again, don't give me which of the following. I stripped the multiple choices off. Let's just go with what is the solution P of t to the differential equation given with the initial condition, all right? So go ahead and try that, and we'll go over the solution in a minute. Okay, my solution is P equals 10 minus E to the log of 6 minus T. I guess you could also say this is 10 minus e to the log of 6 over e to the t, or 10 minus 6 over e to the t, or 10 minus 6 e to the negative t. All those are equivalent, all right? All right, now if you had anything like that or mathematically equivalent, you're good to go. If not, then let's talk about it. All right, so we've got a differential equation and with initial conditions. So shall we say P at t is initial plus integral? And the answer is no. No, no, no fundamental theorem if it's a differential equation. So instead, let's figure out how can we separate the variables here. Now, I don't know about you, but this is kind of weird. This is a little different than I'm used to. I'm used to just doing multiplying and dividing here, not adding or subtracting to get this. And so if you were thinking, how do I do the algebra to get the p's and dp's together, that I could understand. It would be logical if somebody said, hey, multiply both sides by dt, and that definitely helps you here, but that's bad. And so I guess you could then get the dt's on one side, 10 dt minus p dt, and divide over 10 minus p. And that would work. But I think a more expedient way to be doing this would have been just to say subtract the p over and divide by 10 minus p and multiply over dt. All right. Either way, you're going to get the same differential equation with separation of variables. All right. So now let's proceed on with the integration. We integrate both sides. This is dangerous. You guys have been around the block, so you know the danger, I hope. But there is a function within a function component to that because it's subtraction that you have to be aware of. If you were to actually formally u sub, it would be more like negative dp over u and negative log of u and negative log of absolute value of 10 minus p. Now, if you got that without u sub, that's okay. You don't have to show the u sub, but you definitely have to be aware of the negative problem in there. If you just said log of 10 minus p, shame, shame, shame. All right, so negative log of 10 minus p equals t plus c. It's good form. Actually makes your life easier if you use the initial right away. So let's do that. At time 0, p is 4. Time equals 0, p equal 4 is used. Then we get something like negative log of 6 equals c. So if we then go back and put that in, negative log of absolute value of 10 minus p equals t minus log of 6. Now, it's typical that you solve for p. They'll usually say in the question, solve for p as a function of t. So you need to get p by itself. Do it slowly. Log of absolute value of 10 minus p equals log of 6 turns positive, t turns negative. Exponentiate absolute value of 10 minus p equals e to the log of 6 minus t. You could use some exponent rules to change that if you want. Absolute value, dump it, and you get a plus or minus e to the log of 6 minus t. And then I personally think of this as moving the p over here and the e over there. So p is 10 minus plus, if you want to get fancy. And then now we need to use the initial condition. At time equals 0, p is supposed to be 4. Well, if this is 0, then this becomes e to the log of 6, which is 6. The only way 10 minus plus 6 is going to be 4 is if it's minus. So we use minus, and we decide p is 10 minus e to the log of 6 minus t. All right, that's it. Let's go on to this guy. Pause and give it a go. Okay, so for this one I have v is 400 e to the negative 1/20th t. If you agree, move on. If you disagree, let's talk. This guy, when the rate of change depends on the dependent variable, then it's implied exponential growth. They do not want you to take the time to show separation of variables and get to that. Please go straight to that. The volume of the glacier is 400 at time 0, implies that it's 400 e to the kt. And last but not least, at the moment the volume is 300, the volume is decreasing at a rate of 15. So that implies that when volume is 300, the rate of change is negative 15. So we're talking in the dv dt. I think you'll agree we want k now, yeah? You're not supposed to go here to find it. Go back to this equation and plug in negative 15 and 300. And that's where that came from. And so that's where my answer came from, right? All right. So let's go with free response. Take 15 minutes or so to go over this, and we'll check your work in a second. Okay, let's see how you did. Just throwing the answers up real quick, and then you can decide how much you want to watch over. I have, this is 6, this is 0, this is 3 with units, liters per month. This I have is 2 minus 2/3 f times 1/3 f, 6 minus f, and this I have 45/8 liters. Okay, or 5 5/8 liters. All right, let's see how we did. All right, so we're talking logistic growth. The equation is pretty much in the form we like it to be. And so I first sketched a graph saying how much fertilizer at time. Obviously it matters the variables you use. Use the variables you're given. I know we think population generally, but this is using F, so use F, don't use P. All right. Now I know the carrying capacity is 6, and the shape typically looks something like this, yeah? But reading on, it says that at time 0, now normally then, sorry, not normally, the max growth rate, that inflection point happens at half the carrying capacity. But in this case, they say at time 0, you're already at half the carrying capacity. So my graph only had this part, and I said at time 0, it's already at that idea here, all right? So we're looking at that, and here we go now, L at T. All right, so as time goes to infinity, F, the fertilizer amount, approaches the carrying capacity, which is 6. I don't think I needed units on these. As time goes to infinity, the growth rate, or the slope, approaches 0, and that's why the second is there, yeah? All right, so that one probably went fine. B, find the value of df dt at the time when f is increasing most rapidly. I read this twice. Didn't get it the first time. So find the value of df dt at the time when f is increasing most rapidly. It doesn't say find when f is increasing most rapidly, and it doesn't say find f. It says find the rate of change. So I think you'll agree f is increasing most rapidly when f is half the carrying capacity, which in this case is 6. So when f equals 3. Now that's not why my answer is 3. That's if you said that my answer is 3, then that's why. Then you probably have 3, but you don't really have credit because you didn't find what you were looking for. That's an f value. F is 3. The question is, what's the value of df dt when f is 3? So if you throw 3 into that equation, it's 1/3 of 3 times 6 minus 3. That's 3. That's where I'm coming from. All right? And the fact that those both turned out to be 3 is coincidental. That's not always the case. All right. Using good calculus technique, let's take the derivative with respect to t of df dt. And so take the derivative with respect to t now, t of 1/3 f 6 minus f. Okay, again, we're taking the derivative with respect to t, not f. So when I take the derivative of the right-hand side, you know what, I don't want to use the product rule, so I'm going to use distribute, I get 2f minus 1/3 f squared, yeah? Now when I go to take the derivative, I have a mistake. I should have had parentheses around that, doggone it. All right, now when I take the derivative of f, or 2f, it's 2, but then the derivative of f with respect to t, so that's df dt. Now the derivative of this guy, that's negative 2/3 f to the first, but then again times the derivative of f df dt. So let's call that 2 minus 2/3 f, and df dt gets factored out, and they say in terms of f. So I can't leave df dt in there. I have to put in what is f equivalent to, and that's where I'm coming from with this 1/3 f times 6 minus f, all right? Whatever that is. All right. And I didn't clean it up. I just didn't see why. I don't need to find the concavity at a certain point, so why not just leave it? All right. Using Euler's method, starting at time 0 with 2 steps of equal size, approximate the total amount of liquid fertilizer at 1 month. All right. So the change in time, I'm trying to get from 0 months to 1 month in 2 steps. So I'm going to make half-month steps. Step sizes are half. Show the computations that lead to your answer. Is the approximation over an estimate? Oh boy. So let's do part 1 here. Actually, I might need to clean up the second derivative, but we'll see. All right. So part 1, at time initial, which is 0, f initial is 3. Cool. At time 1, which is a half a month away, the first iteration would be f1 is f initial plus df dt at the previous time of 0, population of 3, times a change in time, or a step size. All right, so the initial is 3. The rate of change at 3, I think we already found that in part B, was 3 times a half, And so 3 plus 3 halves, the 3 plus 1.5 is 4.5, or 9 halves, yeah? At time 2, or the second iteration, which is 1 month away, the fertilizer would be approximately, and I'll deal with the approximation in a minute. I wasn't sure what to call these equals or not. Euler's method is equal, but I'll just put the approximation in my final answer. So F1 plus df dt at time 1/2, f equal 9 halves at the previous values times delta t. So that's 3 plus, now I need to actually calculate df dt at 9 halves. So I'm looking at 1/3 of 9 halves times 6 minus 9 halves for df dt times delta t, don't forget delta t, of 3 halves. Now, on the AP exam, you could actually leave it like that. You can leave arithmetic unsimplified. But I'm going to go on and say something like, if I take 3 halves times 3 halves, let's just go 3 halves times 12 halves minus 8, that's 3 halves times 3 halves. That doesn't look familiar. Oops. Delta t is 1/2. I don't know what I'm thinking. 1/2. All right, so that is something like 3 plus 9/8. And why am I so stupid? F1 is 9 halves. 9 halves. 9 halves plus 9/8 is what? 36/8 plus 9/8. That's where I got 45/8. All right. And then finally, part 2 is the approximation an over or underestimate. Give a reason for your answer. Over underestimates in Euler. Euler is like tangent lines. So when you have a curve that is concave up, a tangent line will underestimate. If you have a curve that's concave down, a tangent line will overestimate. So you need to talk concavity. So the second derivative, which is 2 minus 2/3, I don't know if I'm going to need to clean this up, times 1/3 f 6 minus f. What's the sign of this on f's between 3 and 45/8? Hopefully it's concave up or down the whole time, otherwise I know there's going to have a real problem. All right, so for numbers in this range, even at its biggest, 45/8 would be 15. At its biggest, 2/3 of 45/8 would be 15/4. And no matter what, this is going to be either 0 or negative. Right? Okay. This will be positive, and this is positive. So overall, the curve, second derivative is negative, and so because of that, the curve must be concave down. I would conclude that Second derivative is less than 0, so Euler will overestimate the true value. Right? And there you go. Let's switch gears and go to this bad boy here. Let me see what time I have here. Okay, this one is a butt kicker. Do your best and we'll go over in a minute. All right, if you're like me, first time I did this, A was probably fine and B kicked my butt. So we'll talk about it. This is the hardest one I could find. So let's see how it goes. Find the interval of convergence. So the interval of convergence on this bad boy by, oh, actually, hang on just a second. Let me get the answer so you can check your work. You might be fine on A and just need to see B. Pause for a minute. Okay, here we go. So, sorry, my answer to A was negative 1/2 to 1/2 inclusive of the right endpoint. All right, if that went well, then go on to the next part. If it didn't go well, then here we go. You'd start with the ratio test. And that yields something like this. I'm going to ignore the negative 1 to the n plus 1 and go 2 to the n plus 1 and x to the n plus 1 separately over n plus 1 minus 1 times the reciprocal. 2 to the n, x to the n. If you divide out 2 to the n, leaving you with 2 to the first, divide out an x to the n, leaving you with x to the first, and then take the limit of n minus 1 over n, which goes to 1. Then you get 1 times 2x. That's less than 1. Implies that 2x has to be between 1 and negative 1, so x is between negative 1/2 and 1/2. All right, now the endpoints. At x equal negative 1/2, the series becomes something like negative 1 to the n, and negative 1/2 times 2 is negative 1 to the n over n minus 1. That is the same as 1 over n minus 1. And as far as my work, I said that diverges by comparison to the harmonic series. You could prove that, and if I had time, I think on the AP test I would go back and prove that, but I think I would save this and let that go and move on to something else and come back to it with time. X of 1/2 is negative 1 to the n. 2 times 1/2 is 1 to the n, which is just 1. Therefore, this is like an alternating series. This one I did say this is alternating. The limit of the terms, or the terms approach 0, and the terms decrease in absolute value. So it conditionally converges. And that's why, therefore, I included positive 1/2, but not negative 1/2. All right. B. Now, B is a humdinger. So here we go. This is like an identity. Anytime you try and verify a differential equation, you're really trying to treat it like an identity. Show one side can be made to look like the other. Common math is you work one side, not both. And like trig identities, it's typical that you look for the more complicated side and work that side. Now this is going to be rough, and some of you might not even know what to do, what to get started, but I'm going to make series for the left and try and show somehow that it's like a substituted harmonic series with a 4x squared factored out eventually. And we'll see how it goes. All right, so here's where I started. Based on the series they gave me, y is 2x squared minus 2x cubed over 2 plus 2x to the 4th over 3. Generally speaking, negative 1 to the n, 2x to the n. over n minus 1. Now I'm trying to build out that left side, so now I'm going to find y prime. Y prime is the derivative of these. So let's, I'm going to take these numbers and variables separately. So the derivative of this would be 2 squared is the coefficient, and then the derivative of x squared is 2x to the first, minus 2 cubed is the coefficient, the derivative is 3x squared, still over 2, plus 2 to the fourth times 4x cubed over 3. And eventually, generally, negative 1 to the n, 2 to the n, and n, x to the n minus 1 over n minus 1. All right. Now you can see what we're trying to build up is xy prime. So I'll call xy prime then that multiplied by an x, so every x raises by 1 power. So 2 squared times 2, guess I could clean that up. Oh, that's right. And x squared minus 2 cubed times 3x cubed over 2 plus 2 to the fourth times 4x to the fourth over 3. Generally, negative 1 to the n, 2 to the n, x to the n over n minus 1. Now, it says to take the, I'll call this equation 1, xy prime, and subtract y, which I'll call equation 2. So if I take my equation 1 minus equation 2, then these guys are like terms. And so 2 squared times 2 minus 2 squared for this coefficient minus this coefficient, x squared is my first. Plus this guy, so negative 2 cubed times 3 over 2 minus 2 cubed over 2 x cubed. Maybe I'll do one more. This guy is 2 to the fourth times 4 over 3 minus 2 to the fourth over 3 x to the fourth. Generally speaking, it's negative 1 to the n, 2 to the n over n minus 1 minus negative 1 to the n, 2 to the n over n minus 1 x to the n's. Let's see what we got there. All right. So let's do some cleanup because this is a mess. So if I look at this, this is 8 minus 4, so that's 4x squared. Now, starting to, let's see something here. So this is plus, what do we got there? So that's negative 24 halves and negative 8 halves. Actually, I think it's plus 8 halves because it's minus this, and this was negative, so it's plus 8 halves. So negative 24 halves plus 8 halves. Negative 24 halves plus 8 halves is negative 16 halves. So that's negative 8x cubed. Cool. What do we got here? This is, let's just go with 2 to the fourth minus 3 factored out. 16 thirds times 3 is 16 plus 16x to the fourth. Beautiful. This, if we factor out negative 1 to the n, 2 to the n, and n minus 1, we're left with n minus 1 x to the n. What? All right. Cool. Now, in order to try and build what we're getting to, let's factor out a 4x squared, and we'd have 1 minus 2x plus 4x squared, and so on. Now, dang it, because I'd taken out a 4x squared, now x to the n's, not gonna match. Yeah. I tell you what, let's just, rather than write the general here, let's just write the general for our pattern. Remember, we could do that too. So let's talk about this. Looks like there's a 2 going on each time, and it's the same as the power of the x, yeah? So it's a negative 2x to the nth power. Well, that is the series for 1 over 1 minus x with negative 2x, and so boom, 4x squared over 1 plus 2x. Man, that was killer. Wasn't that fun? All right, cool. Let's pause. All right. I'm running late here. I have a pre-calc test soon here, so I need to go. Find the average value of the function. Average value, remember the idea is if you have a curve like this, there is a place, there's a y value where the amount of underestimating the y values and the amount of overestimating the y values are about the same. So I think conceptually it comes from equating to a rectangle, the area under a curve, to an equivalent rectangle, and then solving for the height of the rectangle. But that's the idea. All right. You know all this stuff to death, I believe. This is displacement or change in position, and last velocity is positive, and then it's also distance. This integrating speed is distance x initial plus the change in position is position at any time, and so on. All right. Accumulation function, integrals are accumulation of change. Whether it might be. So I remember just integrating a rate of change gives amount of change. So if you integrated, you know, the rate at which the tree trunk was growing, then it would give you the amount of tree trunk change. Integrating a rate of change gives an amount of change. Area between curves, x and y. Remember that when you have a region and you draw rectangles this way, the base is delta x, the height is f minus g or whatnot. And if you draw rectangles this way, then you're using y as the variable of integration, and it's right minus left. Remember, area should be positive, upper minus lower, right minus left makes positive. Multiple areas, you're good. Volume of known cross sections. Remember, for all these, when you do cross sections, it's prisms. So this is the height of the prism, this is the area of the base. So they're all volume is area of the base times the height. For squares, the area of the base, oh sorry, let's go back. The height is either dx or dy, depending on if the cross sections are parallel to the x-axis, perpendicular to the x-axis, parallel to the y-axis, perpendicular to the y-axis. Draw a picture, all right? For squares, area of the base is side squared. For rectangles, area of the base is base times height, and that could be a couple different variations. They could say the height is twice the x value, or what. It could be a lot of different things. Semicircles, the area of the base is the best way to go is instead of 1/2 pi r squared, think pi over 8 diameter squared. And for equilateral triangles, it's usually area of the base is 1/2 AB sine C is the best way to go because that simplifies to root 3 over 4 side squared. All right, and then isosceles triangles, right triangles are possible, I guess. All these deals are volumes of revolution. Draw a picture. Make sure you can use shells or washers or discs. Always use right minus left and upper minus lower to get positives. And arc length is 1 plus the derivative squared from one to the other. It could be functions of y, yeah? All right, hypotenuse, Pythagorean theorem sums. All right, so would you try this last? No short response. You guys killed the multiple choice problems on this, so I didn't see the point of wasting your time. So would you just do this free response and we're going to be done? Okay, let's see how you did. I don't know if you remember this, but this is the calculus definition of natural log. The area under the 1 over x curve from 1 to a certain point is, natural log of x from 1 to k, which is natural log of k minus natural log of 1. Natural log of 1 is 0, so it's natural log of k. My answer to the perimeter question was, let's just take your pencil and walk around it. What's that length? Well, if this is the 1 over x curve, this has to be 1. This is just a distance between k and 1, so it's k minus 1. This is how high you go to get to the function at k, which is 1 over k. And then finally, this curve. Now that's an arc length question. From 1 to k, the arc length of 1 plus the derivative squared, and the derivative is negative 1 over x squared. And they said leave it in terms of an integral. And then finally, my answer to the last one is it did converge, and it was finite, and therefore and 1. This was the idea. If I take this region and let k grow without bound and revolve it around the x-axis, then you get this forever moving on kind of thing, and disk is the way to go. So the volume is the sum of many of those disks. The radius is the function. The height is the thickness of the disks, which is dx, and the bounds are from 1 to k. And if k increases without bound, then I can integrate x to the negative second, which is negative 1 over x, and evaluate, which is negative 1 over k plus 1 over 1. But as k gets big, 1 over k gets small, and it goes to 0 plus 1 is 1. And therefore, the volume is finite. Quod demonstratum. Right? Or however you say it. Sorry, Latin people. All right, that's it. Have a great day. I'll talk to you tomorrow.